afternoon, students. I'm Chaitanya, Assistant Professor in Mathematics, working in Institute of Aeronautical Engineering, located in Dundigal, Hyderabad. Today, our topic of discussion is interval estimation. In the last class, we have discussed about point estimation, which is a part of estimation inferential statistics. Now, today we are going to continue the lecture with one more important aspect called interval estimation. Okay, let's look into the detail. An interval estimator of a population parameter under random sampling consists of two random variables, which are called the upper and lower limits of the interval estimator, whose values decide the intervals expect to contain the parameter estimate. Let us try to understand these lines. Under estimation, we always try to estimate the value of a parameter of the population. Okay, suppose this rectangle represents the population on which we are interested to study. Okay, the population which we are interested to study. And to describe the populations, we'll use some parameters like mean or median or mode or standard deviation. There are several parameters which will describe the structure of the population. So let us suppose that mu is a population parameter. Now we are trying to estimate the value of mu basing on the sample that is support of the population and its mean, that is x bar, or sample statistic x. So while estimating mu with x bar, there might be little difference or discrepancy. Okay, that means our estimation may not be exactly equal to the original value of the parameter. It may differ. So generally, we'll try to represent the value of mu as an interval. That means if you say that mu lies between interval a and b, that means we are estimating that the value of mu is going to fall between the numbers a and b, which is called interval estimation. Unlike the point estimation, where we have tried to estimate the value as a single number, like average IQ of the aeronautical engineering students is 80 out of 100. This is called point estimation. But if you state that the average IQ of aeronautical engineering students will range from 75 to 85, that is called interval estimation. So, in general, the interval estimation is nothing but specifying the thresholds or the range between which the population parameter value is going to be fallen. Okay, so that is called interval estimation. Instead of estimating the value as a single number, we'll try to estimate the value of the parameter as an interval. That is called interval estimation. Interval estimates all the ranges all ranges in interval estimator can assume. Each interval estimate states the range within which a populator parameter probably lies. So, an interval estimator can be assessed to accuracy, precision. That means there are two important things which play an important role in interval estimation. That is accuracy. That means how accurate we are in estimating the interval of mu. That is estimating the interval of mu. Are we attaining the maximum accuracy? For that, we will use the confidence level concept, of course, which we are going to discuss in the few minutes, in the next coming minutes. And one more thing which helps us to decide the accuracy or to assess whether we are estimating the population parameter correctly or not, that is the marginal error or the maximum error. So there are two things. One is confidence interval and second one is maximum possible error, which helps us, drives us towards estimating the population parameter value correctly or more precisely, more accurately. Okay. Now, here, before going to the estimation problems or interval estimation, I want to discuss some important properties of estimation. Generally, every estimator is nothing but the formula, the mathematical formula, with the help of which we are trying to estimate the population parameter. That means to estimate the population parameter, we apply a formula on the sample. The mathematical formula or the mathematical function or mathematical process which we are using to estimate mean, that is called the estimator. So, estimator possesses certain characteristics or properties basing on which will discriminate among the estimates whether which is better, which is relatively better, which functions relatively better, and which is not working, which is not efficient, which is more efficient, which is more consistent, which is less consistent, which is not biased, which is biased. Like that, we'll have certain criteria to distinguish among various set of estimators. Okay, so that means to estimate the population parameter, we don't uh, we don't presume that there is only one estimator X, only one estimator theta X. Actually, there may be several estimators. There will be several formulas or several estimates which helps us to estimate the same population parameter. Like mean, with the help of mean also, sample mean also, you can estimate the population mean. With the help of sample median, we can estimate the population mean. With the help of sample mode, we can estimate the population mean. So there may be more than one estimator. Okay. So in that case, which estimator is treated as best? Okay. For that, we need some criteria. Let us look into this gap. Here, uh, we are using theta as an estimator to estimate the population parameter mu. Okay, we want to estimate mu, population parameter, with the help of the sample statistic formula called theta. Okay, so our value is theta. By using the sample, we obtain theta value. Now, what we are observing that the data, if we draw a line here, we are observing that more data has been concentrated towards right, like 85%. Only 15% of the data is lying towards the left of theta. That means theta is failing to concentrate the data equally on either side of theta. That means the calculated value is not able to spread the data equally on both sides towards its left and towards its right. So that tells us, suppose this is the population mu, okay, and this is theta. That means we are observing that mu, original value, and theta, the estimated value, are not equal. So that says that this is not unbiased. There is a bias. Bias means there is an error. So we say that here theta is a biased estimate. Now let us consider the second graph here. Here, this is our mu and this is our theta, and we are seeing that if you draw the line, the whole data has been equally spread on either side of theta. That is, here 50%, here 50% of the data has been spread on both sides. And also theta is just below mu. If this is mu, this is theta, both are on same. That means here theta is called unbiased because there is no difference. Theta is equal to mu here, that is unbiased estimate. But if you consider the same estimator formula, same estimator theta for the second population, okay, represented by this graph. Here you are observing that only 10% is lying and 90% is on right side of theta. That means theta is not equals to mu, that is the center. Theta is not equals to mu, that is the center. That means theta not equals to mu means there is a bias, there is an error. So theta is not an unbiased estimator of this population. So what did we observe here? Theta is an unbiased estimator of the first population, but theta is not an unbiased estimator of second population. In fact, it is a biased estimation. Okay, so from this discussion, we understood that an estimator theta for the parameter mu might be biased or unbiased. There are two kinds, biased or unbiased. Biased means both sides the data will be stretched equally 50-50, but unbiased means, but biased means one side will have larger data and one side will have very less data. That is called bias. So we have a mathematical definition to describe this thing as theta will be called an unbiased estimator of mu if expectation of theta is equals to mu. If expectation of theta is not equals to mu, then we call it as biased estimate. Okay, now let us look at this. Now we are going to prove that the sample mean is, we are going to verify that the sample mean is an unbiased estimator of population mean mu. That is what we are going to do. That means whenever you try to estimate the population mean with the help of a sample mean, that means if you want to calculate the average heights of IARE students basing on the sample of basing on this sample, that is second year students. Okay, this is only second year, this is whole IARE. Okay, then the sample mean x bar is an unbiased estimator of the population mean mu. Okay, that is what we are going to show. Let us prove this. Yes, now expectation of x bar, I am starting with the definition of unbiased, that is expectation of theta is equal to mu, then theta is called unbiased, otherwise it is biased. So expectation of x bar, which is nothing but x bar means sum of all observations by number of observations, x1 plus x2 plus so on xn by n number of observations, that is equal to 1 by n expectation of x1 plus expectation of x2 so on expectation of xn. Because you know that expectation constant can be written outside, 1 by n comes out, so it becomes 1 by n of e of x1 plus e of x2 so on e of x. Now you know that the expectation of each value, each independent value of a data set is always mu, that is mu plus mu plus mu so on mu. This is for n times, this is for n times, that means n mu by n, that is equal to mu. So what did we prove? We have proved that expectation of the sample mean is always equals to population, which tells us that x bar is an unbiased estimator of population mean mu. That is what we have established. Okay, now here we are going to observe one more graph. There we are going to see two unbiased estimators. Okay, that means there exist more than one biased estimators. Let us see the example. Here, this is our mu and this is our theta, that is the estimate. Here observing that theta is equal to mu, or expectation of theta is equal to mu, because both sides data has been spread equally. Okay. Here also theta, if you draw the line, both sides data has been spread equally, 50%, 50%. Here also 50%. But what is the difference? That means this is unbiased. Here theta 1 is unbiased estimator of mu, and theta 2 is also unbiased estimator of mu, because both are having equal data, equal amount of data on both sides. Here 50%, here 50%. And for the second estimator also, both sides 50-50. So what is the difference that you are observing between the two graphs? Here you are observing that the data has been spread longer distance, that is from here to the tail end, the distance, and from here to the tail end, the distance. And here you compare the distance, this is this tail and this tail. You observe that this is this is bigger than this. That means the spread is more than this spread, and the left tail is bigger than the left tail. That means here the data has been stored in a narrow space, but here the data has been stored in a wide spread space. Even though both are unbiased, we are observing that the data has been accumulated or spread or scattered to a large distance from the mean. The wings are spread here. Here the wings are spread, but here wings are narrow, and hence it is highly peaked. It is balancedly peaked. It is neither too low nor it is low peak. This is high peak. But here the springs are wide, and here springs are wide. So what do you observe? You observe that it is storing the data in a less space, but it is taking large space to store the data. Okay, that means here to store the data, you have to use large space, but here very less space, it is storing the data. That means here we are observing that variance of theta 2 is less than variance of theta 1. Variance means spread, this spread. Okay, and this spread you can call standard deviation, which is leads to that is variance of theta 2 less than variance of theta 1, and hence we declare that theta 2 is efficient than theta 1. Why it is efficient? Because it is storing the data in less space. Less space only, you are storing more data with theta. But with theta 1, you need larger space. That means it will occupy more space in a row. That is why theta 2 is called efficient, and mathematically you will write it as if variance of theta 2 is less than variance of theta 1, when theta 1 theta 2 both are unbiased, to say that which is better, we will take the help of variance. If variance of theta 2 is less than variance of theta 1, we call theta 2 as an efficient estimate of the population parameter. That means when we have more than one unbiased estimator, to pick up the best one, we'll calculate the variance. That means if we have theta 1, theta 2, so on, theta k, these are unbiased estimators of mu. Okay, we'll calculate variance of theta 1, variance of theta 2, so on, variance of theta k, and we'll pick up that variance which is least among all these, and the corresponding parameter will become the efficient estimator. So variance plays an important role in deciding the efficiency among unbiased estimators. Okay, here you are observing a combination graph where you are trying to estimate the population parameter mu x with help of two estimators called theta 1 and theta 2, and you are observing that from theta 1 the radius is this, from theta 2 the radius of theta 2, okay, and the radius of theta 1 is v of theta 1. The radius, that is the range of spread, is v of theta 1. You are observing that v of theta 2 is less than v of theta 1, and hence you declare that theta 2 is more efficient estimator than theta 1. Even though both are unbiased, here also both are equally spreading, 50-50. But even though both are unbiased, theta 2 will be preferred than theta 1 because it is more efficient, because the variance, that is standard deviation, is less than standard deviation of theta 1. Okay. Now we are going to prove a fact that variance of for population mean, we have an unbiased estimator X. Now we are going to verify whether the sample variance will be an unbiased estimator of the population variance or not. If sample variance fails to be an unbiased estimator of sigma square, by modifying it, how we can modify it to make it an unbiased estimator of the population variance. So this is the thing we are going to discuss now. Okay, now, so as a just recollection, E of x bar is equal to E of x1 plus x2 plus xn. we have separated expectation of x1 and we have observed the proof just now. Now we are going to show that expectation of sample variance is not equal to population variance, and hence sample variance will never be an unbiased estimator of population. Before that, I would like to explain few concepts. If a sample of n observations, the usual estimate of the variance is the sum of the square deviations around the sample mean divided by n minus 1, typically denoted by Sx square. That means there are two sample variances. Of course, I'll use another notation instead of this. So suppose we have a data x1, x2, x3, so on, xk. Let us assume this is a data set we have, okay, with k observations. Then we can calculate x bar as sum of all observations by number of observations. Sum of all observations by number of observations. Okay. Now let us take the deviations of each value from their mean. That is x1 minus x bar, x2 minus x bar, x3 minus x bar, so on, xk minus x bar. Now let us square each deviation. That is square, 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 square. Now let us add all these squares. This is called sum of square deviations around the mean. Okay, sum of square deviations around the mean means the difference between the value and the mean. Okay, first value minus mean plus second square, and second value minus mean square, third value minus mean square. Like that, we are taking the sum of squares of deviations of the values from the mean. Okay, now we name it as, suppose we name it as m. M is equal to summation xi minus x bar. Now we are going to write two kinds of variances. First, the original sample variance, that is summation xi minus x bar square divided by number of observations k. Second one, modified variance, that is modified sample variance, that is summation xi minus x bar square divided by k minus 1, divided by k minus 1. So here we are averaging, that is the average sum of squares of deviations averaged, then we get s square, and sum of squares of deviations divided by k minus 1, we get s bar square. This is called modified sample variance. This is called sample variance. Now we are going to prove that E of s square is not equal to sigma square. Instead, E of s bar square will be equal to sigma square. That is what we are going to do. Okay, that means we are going to prove that sample variance will never be an unbiased estimate. But the modified sample variance will be an unbiased estimator of population variance. Let us look into the proof. So first, here I'd like to start with this step, E of s square, which is expectation of summation xi minus mu whole square k by n, right? Because s square is sum of squares of deviations divided by n. Okay, now let us write it as expectation of 1 by n of summation I is equal to 1 to n of xi square minus two into mu into xi plus summation mu square. Okay, plus mu square. By expanding a minus b whole square, by expanding a minus b whole square, we observe that it will be equal to xi square minus 2 mu xi plus mu square. Okay, now, so expectation of s square, which is equal to summation expectation of I is equal to 1 to n xi minus x bar whole square by n, okay, and which is written as expectation of summation I is equal to 1 to n xi minus mu minus x bar minus mu by n whole square. You can write it as S square means sum of squares of deviations of the observations from the mean, that is xi minus x bar whole square divided by n. So we can add and subtract mu. We can add and subtract mu, and hence we get this term. Now, expectation of 1 by n can be written as out, and summation I is equal to 1 to n a minus b whole square expansion gives you xi minus mu whole square minus 2 into x bar minus mu into xi minus mu plus x bar minus mu whole square. Okay, we can write it as like this. Now, by separating the by here x bar minus mu, by separating the summation, we'll get this step. That is, by separating the summation, we get expectation of 1 by n summation of this, summation of this, summation of this, like that. When we separate, we get this step. Okay, now here if you observe, this step is written as same, and here summation xi minus mu, okay, that means you can write it as summation xi minus mu is nothing but summation xi minus summation mu, that is summation xi minus n mu, right? And summation xi is nothing but again n x bar, so n x bar minus n mu, that is n into x bar minus mu. Okay, summation xi minus mu means summation xi minus summation mu for n times, that is n mu, and summation xi means n into x bar, so n common, we get n into x bar minus mu. That is why from this step we obtained this value. Okay, so after separating summation, we got this, and summation x bar minus mu by a whole square means we get x bar minus mu whole square into n by n, because n is 1 by n is separated, n cancels, and hence we get this step. Okay, now this is like 2 alpha minus 2 alpha, this is like plus alpha, so minus 2 alpha plus alpha becomes minus alpha, minus 2 alpha plus alpha becomes minus alpha. So finally we arrived at this step, 1 by n summation xi minus mu whole square minus x bar minus mu whole square. Let us separate the expectation of this summation minus expectation of this summation. Okay, now let us see what happens. Expectation of summation xi minus mu whole square by n, okay, minus expectation of x bar minus mu whole square. This is equal to 1 by n, of course, 1 by n. So this is equal to, this is nothing but the variance definition, so this becomes variance of x. Variance of x means sigma square, we can write it as sigma square, minus 1 by n, this is nothing but variance of x bar, expectation of x bar minus mu whole square will be again equals to sigma square, and hence sigma square minus sigma square by n, that is equal to you get n minus 1 by n into sigma square. So ultimately what we have observed, finally we arrived at we started with expectation of s square and we ended it with n minus 1 by n into sigma square, which says that expectation of s square is not equal to n minus 1 by, not equal to sigma square. That means s square is not an unbiased estimator of sigma square. So the sample variance fails to be an unbiased estimator of population variance. Then how to modify it and how to make it as an unbiased estimator of sigma square. Okay, so how to convert this S square as an unbiased estimator of the population variance sigma square? For that, see, we are introducing the modified sample variance S bar square as 1 by n minus 1 summation xi minus x bar whole square. Now we are going to prove that expectation of S bar square is equal to sigma square. Okay, now see, this is just now we have proved. Okay, and we arrived at this step. So expectation of S square is equal to n minus 1 by n sigma square, not equal to sigma square, and S square is not an unbiased estimate. So now we are going to prove that expectation of S bar square will be sigma square. Okay, let us try that. So first we will start expectation of S bar square, which is expectation of summation xi minus x bar whole square by n minus 1. Now we will multiply and divide with n, and hence we get n by n minus 1 summation xi minus x bar whole square by n. Okay, that means this is a constant. Constant can be written outside of the expectation, that is n by n minus 1 expectation of summation xi minus x bar whole square by n. Okay, so just now we proved that n by n minus 1 expectation of this, that is expectation of s square, that is n by n minus 1 into n minus 1 by n sigma square. We just now proved it. Okay, and n minus 1 cancels, n cancels, the answer is sigma square. So what we arrived at? We arrived that expectation of S bar square is equal to sigma square. Hence S bar square is an unbiased estimator of population mean sigma square. That is what we are concluding here. Now, this is called confidence interval around of the population mean around the sample mean x bar. Okay, what is this formula says? First, let's try to understand. We can write it as at 1 minus alpha level of confidence, level of percentage of confidence. Level of confidence, you can take 95% confidence I am, or I'm 99% confident that I will do this task perfectly. So level of confidence is different as 1 minus alpha. Okay, and corresponding to this level of confidence, we define the interval of estimation of mu, or the confidence interval. The confidence interval of the population mean mu as x bar minus e and x bar plus. That means we are expressing mu, the population mu, as an interval where the mu value will lie between x bar minus e to x bar plus. That means when we are trying to estimate the mu with the help of sampling in x bar, okay, mu will fall with an error x e, that is x bar minus e to x bar plus. So the range of mu will be x bar minus e and x bar plus e with the confidence probability 1 minus alpha. Now what is e? For e, we have a specific formula, that is z alpha by 2 sigma by root n. What is sigma? The population standard deviation. What is n? The sample size. And z alpha by 2 is the normal distribution value, okay, at 1 minus alpha level of confidence. So this is called confidence interval of mu around x bar. Okay, and this e is called maximum error between x bar and mu, maximum possible error between x bar and mu at the given sample size and at the given level of confidence. Okay, now we will understand these things with the help of a problem. To estimate the average time it takes to assemble a computer component, an engineer has timed 49 technicians in the performance of this task getting a mean of 12 minutes and standard deviation of 1.9 minutes. Suppose you are working in a computer software company and they require you to know the hardware things also. That means you should be able to assemble the components of a computer in a correct way so that the computer works correctly. Okay. So, and after training, after going through a training, there are certain students who have undergone the training of hardware components. Okay. And out of so many students, the teach trainer has inspected 49 technicians, and each participant is taking on an average 12 minutes to assemble the computer. 12 minutes to assemble the computer, to join the monitor with keyboard and CPU and the wire networking and mouse, everything, to assemble all the things, internal, external, everything, to build up, to arrange the computer and to assemble the computer. They are taking on an average 12 minutes, okay, with 2 minutes to plus or minus. Okay, that means on an average they are able to arrange everything in the order with an average time of 12 minutes with 2 minutes plus or minus much. Okay, under this question you are asked to construct 99% confidence interval for the average time it takes to assemble the components. So now you have to estimate what is there are thousands of employees out there. So what is the average time taken by the employees to assemble the computers in the whole factory? Okay, you have to estimate the mu as an interval around 49, around the sample mean x bar. Okay, that is called confidence interval, and the level of confidence that means you are assuming that 99% our sample calculation will coincide with the population parameter value. That is your confidence. Okay, now with what confidence we can assert the sample mean does not differ from the true mean by more than 50 seconds. Also, in the second bit you are asked to in the first bit you are asked to construct the confidence interval for the given confidence level. In the second bit, the reverse is given. You are given with E, that is the maximum error. Okay, and you are estimated to find the confidence level. Okay, so how we are going to deal this problem? First, number of technicians we have tested, that is 49. So n is equal to 49. Okay, n is equal to 49. Now, what is the average time taken by each technician in the sample, in the 49 people, to assemble the computer components? That is 12 minutes. Implies x bar is equal to 1 because it is a sample mean. Only 49 people are tested among thousands of employees or hundreds of employees. So this is sample mean, that is 12 minutes you are taking. What is the standard deviation is given? That is 1.9 minutes. 1.9 minutes. You can take it as 2 minutes around. 2 minutes is the standard deviation. Now you have to estimate the interval for mu within which two values the mu is going to fall. Okay, you are going to try to find that value. For that, we need E is equal to the formula maximum possible error. The formula for maximum possible error is E is equal to Z alpha by 2 sigma by root. Okay, this is the formula. What is sigma? Sigma is 1.9. So 1.9 by what is n? Number of technicians you have tested? 49. Root 49. What is Z alpha by 2? It's a table value from normal tables. Okay. So Z alpha by 2 is nothing but at Z alpha by 2 at alpha is equal to 99% confidence. For that, we know that by using the normal tables, we come to know that Z alpha by 2 at alpha is equal to 99% confidence is 2.58. So this is 2.58. After calculating this, you will get an answer. Okay, and then you will tell that what is x bar? X bar is 12. So x bar minus E. x bar plus, that is 12 minus 2.58 minutes to 12 plus 2.58 minutes. So you are telling that the average time of the whole factory employees to assemble the computer parts will be ranging from 7.92 minutes to 14.38 minutes. Okay, so this is called interval estimation. So here we have estimated the population mean time of assembling the computer new as an interval. This is called interval estimation. Okay, now let us look into the second bit. The second bit is, with what confidence we can assert that the sample mean does not differ from the population true mean by more than 15 seconds. Okay, that is, error is equal to 15 seconds. Why error? I told you error will be the difference between the estimated value and the population value. He is saying that difference between the original parameter to E is 15 seconds. 15 seconds means 1 minute is equal to 60 seconds. So 15 by 60, that is equal to 1 by 4th minute. That is 1 by 4th minute. That is expectation. Okay. Now, what is expectation formula? Z alpha by 2 sigma by root n. What is the formula? Z alpha by 2 sigma by root n. Okay. Now, E is 1 by 4. Z alpha by 2 you don't know. You know sigma. What is sigma in the given 1.90 minutes by root n, that is root 49. Okay, 1 by 4 root 49 means 7. So 7 by 4 is equal to Z alpha by 2. Okay, so Z alpha by 2 is equal to 70 means 0. 17. Okay, and 171. Z alpha by 2 is 0.17. Okay, now we will calculate E. We have E, we have Z alpha by 2. Now we are asked to find 1 minus alpha. 1 minus alpha by 2. You can use this formula, is equal to A inverse of 0. Z alpha by 2. Okay, that is equal to A inverse of 0.17. By calculating this value, you will get 1 minus alpha by 2. 1 minus alpha, approximately it will be 96%, you can assume. So, or 96, or what do you say, 48%. So 1 minus alpha by 2 is equal to 0.48. 1 minus alpha is equal to 0.96. So level of confidence is 96%. That is what it is. So the level of confidence we calculated with the help of this formula. Okay, and that is 48%. So by using that, 1 minus alpha is equal to 48% and 1 minus alpha will be 96%, and hence we are saying that the level of confidence is 96% that the employees will assemble within 15 minutes the computer components. So in the next class, we'll see some more real-time applications of interval estimation. We'll solve some more problems. And with that, I'd like to conclude this lecture. Thanks for your patience learning. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.